12. Epsilon in SI units. Epsilon is going to be something bigger than that. And so, for example, it might be 1.5 times 10 to the negative 11. And that would be Coulomb squared per meter squared. Now, keeping track of these numbers becomes a nuisance. And so they took it one step further and they just said, you know what, let's just define this term kappa. That's a kappa, not a K. We'll call this dielectric constant.
That's not a K.
It is not a K, it's a kappa. I put a little bit more curve in my kappas than I do for my Ks.
I'm trying to figure out what's different. Is just that bottom leg, mainly?
That's my K. That's my kappa. All those supposed to touch. That's how I do it. And that is just the dielectric, the permittivity. That's the permittivity of that material divided by our base value, the free space. So this is permittivity. I think I might have misspoken earlier when I labeled that permittivity. And the dielectric constant is constant for a material. It is not a constant for, it's not the same number for everything. Now watch how the formula changes. We have that formula over there when I had nothing in between them. The formula now becomes C equals epsilon A over D. Yeah, big shift. Or kappa epsilon sub naught A over D. And so often throwing dielectric in there is you take wherever there was an epsilon sub naught, you stick in a kappa epsilon sub naught.
Wait, but how does the kappa help you keep track of the numbers?
I'm no longer dealing with exponents. Kappa is going to be some number 1 through this is what you're working with.
Okay.
Finding the dielectric constant for a material, those charts are usually easier to find than the permittivity for a material.
Okay.
All right, so what does the dielectric do?
Sorry, this specific to parallel plate capacitors.
It's just easiest to work with parallel plate capacitors. No, the dielectric constant is going to be true regardless of what type of capacitor you have. Again, another thing I think we've done already, but all right, so if I have a positive and negative plate here, and I got my electric field flowing across, if I stick an insulator in between them, recognize that it's an insulator, so I'm not going to be ripping electrons off, I hope. But I should be able to polarize the atoms. And so I'm going to get, my electrons are going to get pulled in that direction. They aren't going to get ripped out of the atom, but I'll have a negative positive, negative positive, negative positive. It'll sort of look like that. And each of these atoms, which has now been polarized, has its own electric field going in the opposite direction. So my total electric field will decrease. Or, well, it depends on what else is happening. So if I have just 2 charge plates not hooked up to anything, but I've already charged them up, I disconnected the battery. So my charge isn't changing, my electric field will change. So my electric field total will be the electric field from the plates. I guess minus, plus, however you want to look at it, the electric field from the dielectric.
So the atoms all become polarized when you charge the plates?
Yeah, when you put the dielectric in between the two charged plates, the
Mhm.
atoms become polarized.
Oh, okay.
The more polarized it becomes, the higher the dielectric constant, the greater the permittivity. Thus, permittivity is a measure of how a material will react in the presence of an electric field.
Okay.
How do you calculate the electric field from the dielectric?
How do you calculate?
Is that something that's given in a problem theoretically, or is that something that I have to find?
I mean, the electric field from the plates is sigma over epsilon sub naught. Or if I've got dielectric in there, sigma over kappa epsilon sub naught. Sigma is charge divided by area. So area, you can measure it. Charge, well, if I know the voltage and the capacitance, then charge is C delta V, the capacitance times the voltage. And somehow, does that address your question, or were you asking something else?
If we were given a problem, example problem, would we be finding the electric field of the dielectric, or would we be deriving the electric field of the dielectric?
Typically, in a typical problem, I would give you voltage of the battery, size of the plates, distance between the plates. And so if I gave you size of the plates, distance between the plates, you should be able to find the capacitance with nothing in between them. If I gave you a dielectric, I typically give the dielectric constant. So then you could find the total electric field. We'll get to some problems, don't worry. Because I know everybody loves doing the math.
Yes.
Unfortunately, these problems aren't gonna have calculus in them. That's all I'm saying.
That's not what I signed up for.
Well, you know what? We'll do some calculus for you.
Awesome.
And then we'll do some labs also, just for you.
Oh. That's where I draw the line.
Or sent it somewhere. Oh, okay. So let's do a problem. And then we'll assess time and what happens next. So I got a 1 meter by 1 meter plate, or I got two of them, two 1 meter by 1 meter plates. Hooked to, we'll make it a 20-volt battery. Period. Plates are 5 centimeters apart. With nothing in between them. Nothing in between. Plates. I'll just make it specific. And they're parallel plates, which hopefully you pull from context, but you make it explicit. Now, there are certain things that I would ask you to find. You should be able to find the charge on the plates. You should be able to find the voltage between the plates. You should be able to find the electric field, magnitude of the electric field from the plates, the total electric field, and the capacitance. Not necessarily in that order, whatever order it happens to come out. Well, we can't find the electric field until we find the charge. So, and we can't find the, well, voltage we could actually find right now. Because I basically have a parallel plate capacitor hooked to a 20-volt battery. So what is the voltage between the two plates?
-20.
Depends on which way you go. So I'll just make the absolute value 20 volts. My capacitance, it is a parallel plate capacitor. So my capacitance, epsilon naught A over D, which is 8.85 times 10 to the negative 12, times my area, which is 1 square meter, over D, which is 0.05 meters. Should have picked nicer numbers. $17.76. Uh, 1.776 times 10 to the negative 10.
That's what I got.
Units? Farad. All right, so now I know what the capacitance is, 1.776 times 10 to the negative 10 farads. We can now find the charge, because I know the charge is capacitance times the voltage, so that this times 20 gets us something. Let's see, 2, 5, 3 times 10 to the negative 9 coulombs. Anybody else get that?
Wait,
I'm getting to the -8,
Negative 8?
but I could be wrong.
Did you get this to the negative 10?
I think.
Or you use that?
wait, how'd you?
When I put my.
Oh, yeah, I did to the -9 for some
Finding
reason.
the capacitance of the capacitor, I got 1.77 only with the calculators, maybe the 6. Yeah, that's
Okay. But you got times 10 to the negative 10?
yeah.
Okay. So 8.85 times 2, 0, oh, yeah. Okay, 1.77. So this becomes 3.54. All right,
And you got that from multiplying the 20 volts with the capacitance?
yes.
Okay.
Going back to this definition of capacitance is charge divided by voltage.
I got 3.552.
Oh, yeah, there was a mistake here, that should have been 1.77.
Okay, then, yeah, that would. And I also got to the negative 9s. Just,
Negative 9 up here? Yeah, okay, all right, good. Now, so I have this charge built up on the plates. I've got the positive value on the positive plate, just a negative in front of on the negative plate. The electric field coming from the plates is sigma over epsilon sub naught. Well, sigma is just charge divided by area. I know what my charge is now, 3.54 times 10 to the negative 9th coulombs, divided by my area, which is 1 square meter. So my surface charge density is 3.54 times 10 to the negative 9th. That is just horrible handwriting. And then divide by epsilon naught, so 3.54 times 10 to the negative 9th coulombs per square meter. over 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. Which
Around 400, per coulomb.
you got 400
Yes,
newtons per coulomb works.
and, if the area was in 1 meter squared, would you multiply the denominator by whatever the area is?
My surface charge density would have been something other than 1 there, so it depends on how you're working it. If you find sigma first, then you've already taken into account the area. Did that answer your question?
Yeah.
Now, we could have found let's now do total electric field. My total electric field will be the same because there's no dielectric in there, so that doesn't change. But I can also find total electric field using the ED equation, so it's just the voltage divided by the distance between them, which is 20 divided by 0.05, which is 400. Questions here? Wait.
So the units on that would be volts over meters, and that's,
Volts per meter or newtons per coulomb.
so those are equivalent?
Yep.
Okay.
They better be.
What's the difference in Q? What is the symbol over epsilon sub naught by the plates? Yeah, right there.
That's a sigma. That's a
Sigma.
lowercase sigma. That's surface charge density,
Okay.
which we found down here. That's charge divided by area.
Oh, so it just happened to be the same as the Aries one.
Yeah.
Okay.
I probably should have picked different numbers just so that wouldn't happen.
All right. Sorry. Yeah. For some reason I was thinking that was Q. Thank you.
All right. Why don't we take a break here? And so we got an hour and 20 minutes. My original thought was we do this stuff for an hour and then we would do a lab, but I'm gonna push that lab off until Thursday.
Wednesday or Thursday?
Wednesday. Wednesday.
We can do Thursday. I'm fine with that.
Is it an in-person lab?
Yeah, it'd be an in-person lab.
Oh, okay.
But this way we get to do the full lab as opposed to an abbreviated version of it.
That's probably better.
I don't know. I mean, the abbreviated sounds pretty nice.
So take 5. I'm gonna pause on the recording and hopefully I'll remember to turn it back on. All right, so we picked up that recording. Now we'll record this. All right. We're live again. All right. Parallel plates. This is the lab that we're gonna be doing on Wednesday. You're basically gonna take these 2 parallel plates. We're not gonna hook it up to a power supply because the digital multimeter has its own voltage, and so what we care about really is the capacitance. We're gonna put dielectrics in between them of different thicknesses and be able to see if we can figure out what kappa is. I was gonna point to it, but right there we go, capital. So, parallel plates. I noticed that on some of your graphs for that first lab, Excel gave you a slope, usually one significant figure, and gave you an intercept, usually one significant figure. On this parallel plate capacitor lab that you'll be doing on Wednesday, do not use only one significant figure. It's in the procedure, it tells you how many significant figures on one. But it makes a huge difference. Sometimes it makes the difference between having an answer that actually is realistic and having an answer that is impossible. And occasionally, in physics, you want answers that are realistic. All right, let's start to continue this exciting journey. I've got my So a 20-volt battery here, or power supply. Hooked to my parallel plates. We figured out all the great information here. Now we're going to do something different. We're going to stick a dielectric in between.
Sorry, Dr. Fox, would you mind moving the screen? Thank you.
So we're sticking a dielectric in between here. And the dielectric constant of 2. So first off, what will be the exact same? What is not going to change because I stuck a dielectric in there?
The volt.
The charge and the voltage.
Charge will change.
The area of the plates.
Area of the plates will stay the same also. I was thinking of these 5 things right here, but the area will stay